In these sections, that pretty much toward the end of these chapters, we're going to talk about the shearing strain and in relation to shearing stress. And by doing this, we're going to introduce the second half of Hooke's law for shearing, basically relating the shearing strength gamma to shearing stress by similar to Young's modulus. Here G is called the rigidity modulus. Okay. So first one, let's introduce how to measure the shearing strain. In essence, if you look at the two-dimensional patch, here is a square, and this is undeformed. Okay. And under the loading, like showing here, so that one can be seen if you have the shearing stress applied to the two sides of the undeformed patch, then that will be kind of the shearing going to shear off, and not to shear off, kind of shearing the element in deform in this way, okay, into kind of the rhombus-like shape. Sometimes the expressions for deformed shape will be something like this, is kind of in symmetric respect to his diagonal line. And the two expressions, either you aligned the one side fixed or you have a symmetric like this. Basically, the two expressions are identical. The way I can say so, because if you do the rigid body rotation of this rhombus, okay, if you do the rigid body rotation such that rotate by that much angle to align this side to this side, then you will find this one actually will become like this. Okay, so by saying this, basically here in general in different textbooks, they basically adopt either this notation for describing deformed under shearing, or defined, or using this one. Really up to the preference of the authors or in the instructors. And so, but anyhow, for either of these, then here how we measure, how we define the shearing strain. Basically, the shearing strain is these things. It simply is the change in the angle between the sides. Okay. Let's look at these expressions for between the undeformed and deformed shape. So from here, this is a change in angle. Okay, so, and how about for this? For this one, the change in angle is this plus this. Okay, and so here we define the shearing strain using the symbol gamma. So here is our shearing strain that is changing in angle gamma. And for this expression, basically the additions of the two changes become gamma. In symmetry, this is gamma over 2. This angle is gamma over 2. Okay, so from here, we simply define the shearing strain. In relating to the shearing stress, we simply apply Hooke's law, and here you simply take it whatever the shearing strength measured. Okay, so for example, this one indicating is we have the deformed patch in given in the XY plane, and then is deformed shape will be something like here. Here I exaggerate. Okay, so here is what we define the gamma XY. The gamma measured in XY plane, so that is a subscript meaning. And usually this angle is very small. Okay, and here I simply exaggerate, and many textbooks also exaggerate, but you need to keep in mind this angle is very small and usually is the hundredth of a degree. Okay, so and multiply this angle with the certain material properties. Here we call it rigidity modulus, or modulus of rigidity, or simply called the shear modulus. Then multiply that one, we get the corresponding shearing stress. Okay, and in a similar way, we can exercise for this. Basically, that is the shearing strength measured in YZ plane. Okay, so here we have undeformed patch, and then under deformations, and here we measure the angle in the YZ plane. So this angle is gamma YZ. Okay, so you can deduce the situation for this one. So from here we constitute the three additional equations for Hooke's law. And in total, if you remember in the normal normal strain, in the previous sections we have three equations and plus 1, 4, 5, 6, in total 6 equations for describing the generalized Hooke's law. This is a simple example to exercise how to apply the Hooke's law for shearing stress and shearing strain. And this example is basically here we this top and the bottom plate, they are rigid, and meaning they simply acting as to transmit force, but they won't deform. And the only deformable materials is the material in between that kind of being sandwiched. And under these situations and under certain application of the loading P on the top of the plate is simply transform the force to the middle deformable material here. The bottom plate basically fixed to the ground. So under this situation, you would imagine the middle material going to be kind of the sheared, deformed into this. Okay, so I here kind of schematic drawing like this one here. Okay, so that's going to be deformed, be dragging, similar to a fluid in between two plates, similar concept like that one. And then for this case, we, and let me find where is my. So under this case, basically the shearing here, we have the deformations. Here on the top is 0.04 inch. Okay, so basically if you look at this triangle here, and this is 90 degrees, let me plot that at triangle here. Okay, so this point attached to the bottom one, that's fixed, no movement. The top, this point, due to the dragging of the force on the top plate, that moving by 0.04 inch. The height is 2 inch. Okay, so from here, can you see, if we applied our concept, if you could imagine this is the side, one side of undeformed patch. Okay, so let me plot the undeformed patch, and then this is the one side of deformed patch. So by adding this kind of additional lines to form the side, can you tell this basically is gamma? Okay, so under these situations, the basically gamma is equal to arctangent and 0.04 divided by 2. And again, because this number is very, very small, so arctangent can be simply approximated by this number, so that is 0.02. Okay, so gamma equal to 0.02. Once you form the gamma, and here we given the stress, so basically G times gamma equal to stress. So basically stress meaning the average, the force per unit area on the top here. So basically once you have the gamma, the tau multiplied with area, the area is the area where it's acting, so basically that is the area of the top plate, and that will be equal to P. So from here you can decide the P. Okay, so area here is 8, A area equal to 2.5 multiplied with 8, and so from here we can decide determine the magnitude of P. So this page showing the detailed calculations, and that is for these sections.